Okay, good evening. Hello, everybody. Welcome to today's ISGC seminar talk. It's a pleasure to introduce to you Seong Park. He is currently a professor at Yonsei University and did his PhD in 2002 at Seoul National University, both in Korea. And he will talk to us about Higgs inflation. And with that, I hand over to you. If you have questions, please feel free to interrupt during the talk. I will monitor the chat. So if you have questions, please also drop them here. And with that, the stage is yours. Thank you very much for giving this talk.
Thank you, Torben, for a nice introduction. I'm very happy to give this talk today. So I'm going to review the Higgs inflation, basically, and I want to show you my vision about this direction. Especially, I want to talk about the particle physics and cosmology connection. And I believe Higgs inflation is pretty good framework. We can talk particle physics and cosmology all together. And also the observational and experimental opportunities would be pretty good. So I just want to deliver that kind of message today. All right. So before starting, I put the picture of Yonsei University. It's a nice looking campus located in a convenient place in Seoul, pretty close to the city center. And if you come to visit Seoul, please let me know and visit Yonsei University. I'm going to show you the campus and let's have Korean barbecue together. Okay. So contents. So first part, I want to talk about the inflation the way I understand. Okay. And then I'm going to move on to the Higgs inflation and discuss pretty general framework about the Higgs inflation, starting from non-minimally coupled theory of the gravity, F-all gravity, and Higgs all-2 model, and also discuss a little bit about the phenomenology, focusing on primordial black hole and gravitational wave. And if I have some time, I'm going to discuss more about the reheating and leptogenesis, but I think I want to focus more on the basics. Okay. And as Torben already told you, please interrupt me at any moment if you have any questions. I'm happy to discuss. Okay, some of references. So I'm going to share just this file to you later. So you may want to see some of the papers I'm going to use this talk. Okay. So inflation. As we all know, inflation was suggested sometime in 1980s, and that provides initial conditions for hot Big Bang. That's the way I like to say about the inflation these days. Okay, initial condition for the Big Bang is provided by the inflation. So by the inflation, we can have causally connected patch of our universe that is relevant part of our universe, of course. And by the inflation, the space becomes isotropic and homogeneous. So we do have pretty good understanding why the CMB looks isotropic and homogeneous. Okay. And also we can understand why we don't observe any monopole or cosmic defects and so on in our patch because of the inflation. Okay. As a bonus, because of quantum fluctuations during inflation, and those fluctuations will become the seed for the structure in the universe. So kind of free lunch if we accept the inflationary framework to understand the early part of the universe. Okay, so this is the inflation. And as we also all know, there are many models. Okay, since 1980s, theory space grows fast. So theory space inflates. Even these days, number of new models are increasing all the time. Okay, I don't have to mention what are the models, but there are models. If some of my students talk to me, what kind of inflation model I like the best, then yeah, usually I just usually tell them there are many models. You should have chosen by yourself. There's no rule. But for me, Higgs inflation is a very interesting framework. So sometimes I recommend them to consider Higgs inflation, but there are models, many models, many more models. Okay, so there has been inflation in the theory space. That's the first message. So in these circumstances, what kind of model we should focus on, right? To build a successful model of inflation, we need to realize several very important facts about the inflation. Okay, in particle physics, usually we want to introduce a scalar field to explain the inflation. Okay, vectors and fermions doesn't work basically. Fermions cannot be a coherent part of the whole universe, so it cannot be used. And vector usually generate anisotropies that we don't like. So scalar is almost unique opportunity to be the inflator. Okay, so during the inflation, we usually take scalar field, coherent scalar field during inflation, and having a very flat potential in the slow inflationary framework, and that slow roll framework accommodate a large number of e-foldings, like 60 e-foldings. So before the inflation and after inflation space, the universe becomes e to the 60 times large. If we do have this e to the 60 e-foldings, we can understand why universe is homogeneous and isotropic. And also we can understand why no monopoles are in our pitch. Okay. And then finally, we need to realize a reheating of the universe. So the energy stored in the inflaton part, inflaton potential should convert into the particles and radiations. So when we talk about inflationary models, we need to explain flat potential, slow inflation, and the reheating. So reheating takes place and decoherence takes place. So after the inflation, inflaton field becomes inflaton particles and also radiation and matters and so on. Okay, so this is the most important part of the successful inflationary models in particle physics. In 1922, Friedman successfully derived this Friedman equation that explains how the rate of the expansion of our universe when the given energy density rho is given. Okay, and K is the intrinsic curvature, and in inflationary models usually K is 0. So A dot square, the scale factor, the rate of the scale factor squared is given by the energy density rho and the scale factor squared. So when we introduced Hubble parameter, h squared, that is the ratio of A dot over A squared, and then by considering this Friedman equation, we can actually solve this Friedman equation when the energy density is constant. Okay, when energy density is constant, Hubble parameter is constant, and by solving this Hubble definition of the Hubble parameter, we can solve the scale factor. And this scale factor has exponential factor here. So e to the h is Hubble parameter and the time difference. Okay, so by having this basically rho, the constant rho, the constant energy density, we can realize inflation. And by having this constant energy density, we can realize actually eternal inflation. Inflation never ends, just exponentially expanding all the time. Okay. However, in reality, we actually need not really constant rho, but a rho dot is just small. That's the requirement we want to realize. In that case, Hubble parameter is slowly varying, and we can actually solve the scale factor, and that is now given by the integration of Hubble parameter over the time. Okay, So this is usually called slow roll inflation, and our goal is to realize this slow roll inflation for realizing particle physics-based inflation model. So again, now in particle physics, we introduced a scalar field that is called inflaton, that is flat potential. In this case, the energy density is nothing but the potential itself. Okay, because of this flatness, the kinetic term is negligible. So if we neglect the kinetic term, the energy density is just given by the potential. And if the potential is constant or very slowly rolling and potential is constant, so then we can realize the inflation. And that slow rolling is parameterized by two slow roll parameters, epsilon parameter and eta parameter. And epsilon parameter is first the derivative of the potential squared, and the eta parameter is second derivative of the potential. If these parameters, epsilon and eta, are small, we can realize slow roll inflation. Okay, that is requested. Once we can calculate these slow roll parameters, we can calculate the cosmological perturbation and then obtain the observables. The most important observables are spectral index NS, tensor to scalar ratio R, and the non-Gaussianity parameter FNL. Okay, and they are all very well measured these days. So by comparing these observables with the predictions from a particular model here means particular potential, and then we can test the inflationary model. Okay. So this is a particle physics model building of the inflation. Okay, now I want to change my gear to more particle physics. A very special choice is Higgs itself. So this Higgs is the standard model Higgs, SU2 doublet Higgs, that is introduced to solve the electroweak symmetry breaking and also the masses for the elementary particles, as we all know. And I want to emphasize this, the standard model Higgs is the only observed elementary scalar up to today, okay? Most probably that is elementary. And there are models of composite Higgs, but data is really consistent with elementary so far. So let me take the Higgs, the standard model Higgs, as the elementary particle. And in the standard model, Higgs doublet is doublet of SU2, a singlet of SU3 color, and it has a hypercharge 1/2. So once you give these quantum numbers for the Higgs, you can parameterize the Higgs in this way. So here G plus is located upstairs of the SU2 doublet, and that is Goldstone boson. This guy will be eaten to the W bosons. So this will not be the physical degree of freedom later. Part of the longitudinal polarized part of W. Okay. And in downstairs, I have 3 components: V, which is the vacuum expectation value of the Higgs, and H is the standard model Higgs degree of freedom, Higgs scalar. Okay, and G is Goldstone boson. Okay, I forgot I here. And this guy is also eaten by the Z boson. So the longitudinal mode of the Z boson here. So in physical, in this Higgs doublet, I have one physical Higgs scalar degree of freedom, which will be the power of the inflation. Okay. And once I have this SU2 doublet Higgs, I can write down the Higgs potential in this way. This is the only way I can write down the Higgs, okay? Gauge invariant combination of the Higgs. Here, lambda is Higgs self-coupling constant, And V here is coming from this V, the vacuum expectation value. So in this Higgs potential, I have only two free parameters, lambda and V. They are measured, okay? V is measured by the Fermi constant. It was already known in 1930s. That number is 246 to 2 GeV, okay? And lambda is measured by the mass of the Higgs, okay? The mass of the Higgs is measured to be 125 GeV, okay, from the CMS and Atlas experiment. And by putting V here to 46 here, I can get the lambda at the electroweak scale. So Higgs, in the Higgs potential, Higgs self-coupling is turn out to be 1/8. Okay, more precisely, it is 0.13, blah, blah. Okay, this value is pretty well measured nowadays. So having all these things, now I can write down Higgs potential in this way. So Higgs potential has the quartic term, and the coefficient is 1/32 because the lambda is 1/8. And the Higgs cubic term, 246/8 GeV, and Higgs mass term, 125 GeV. So this is the Higgs potential, our standard model Higgs potential, okay? It is important to notice only third term, 125 GeV, is measured, okay? And this cubic term, 146/8 and 1/32 for the quartic, they are all predicted from the standard model, okay? And I always want to have more heavier, the higher energy colliders, because I really want to test this part of the Higgs potential. We never have measured Higgs cubic term and Higgs quartic term so far, so they are theoretical predictions. So we want to really test this part. This is very good. Okay, so what is good? Okay, I also want to tell you that the standard model Higgs is well established. As we maybe you have seen this plot many times. So if the Higgs, the observed Higgs, is really responsible for all masses of elementary particles, mass of each particle is proportional to the Higgs VAV. In that case, you can see a linear relation of the mass and the VAV. So in this plot by the Atlas, you can really see the mass and coupling the plane, and you can see this nice linear relationship. So by seeing this, yeah, we are confident we have observed the Higgs. So Higgs is real guy, and we want to use this Higgs for the inflation. Okay, let's see. So now the question is, can this Higgs be the inflaton? Okay, and the answer is no and yes. So what does it mean? So no. The first, if I take the Higgs potential like this, okay, I told you this is the measured Higgs potential. And by this Higgs potential, you can calculate the slow law parameters, epsilon and eta, okay? And they are, you just plug in this here. And by taking the large field value of the Higgs, you basically keep only the quartic term. The quadratic term and cubic terms are smaller than the quartic term when the Higgs field value is large, okay? In that limit, you can realize the epsilon and eta small. So this is the region, the parameter space where you want to play for the inflation, okay? So these are calculated from the quartic term. And then by putting this epsilon and eta in this, the spectral index NS and R, you can calculate NS is nothing but 1 minus 24, 1/h square, and R is 192 and Planck square over the Higgs square. From here, you can see the nice relation. R is 8, 1 minus NS, okay? This is the result from the standard model Higgs. In that case, you can just plugging in the spectral index 0.965 obtained by Planck satellite experiment, then you can get this aspect, the tensor to scalar ratio, that is 0.28, okay, which is 3 sigma away from the acceptable parameter of the tensor to scalar ratio. So this is basically ruled out. You cannot explain the inflation by this Higgs, okay? Interestingly, you can actually see that all chaotic inflation models are ruled out. Here, the chaotic models, I mean, the potential is given by phi to the n, the power law potential. Whatever power n, you are out of the acceptable range of the observation. So here, I show you the NSR plane again. In this NSR plane, only this part, the blue part and green part are partly allowed. After the BK18, the A10 and BAO, only this the blue part is acceptable. So tensor to scalar ratio is acceptable only below 0.03 or 0.04. If you take 1 sigma, that's even more stringent, and acceptable upper bound is 0.02. Okay, and just compare the value I got for from the Higgs, or 0.2, that is way above here. Okay, so this is basically not acceptable. And all chaotic inflation models are not acceptable. Okay, indeed, if you are looking at this observational situation more carefully, almost all models are ruled out. Very interesting. There are many, many models in theory space, but most of them are already ruled out. That's very interesting.
Hi, Parker. I have one
Yes.
question.
Yes,
If
please.
you consider the general polynomial potential is also ruled out,
Yeah, they are all
does that mean that if I consider phi square plus a phi 2/4,
yeah,
this kind of missed
pi is here, pi 2/3 is
phi
here.
square, or say phi
is
square
here.
plus a phi 2/4 simultaneously.
You mean yeah, if you sum
Yeah.
them up. Okay.
Yeah.
Yeah, that's also pretty hard, because okay, here in chaotic models, usually the field value itself is large. So
Yeah.
maybe if you even sum them up, pi to the 4 and pi to the square, and the mass you need to consider, right? If the field value of the phi is larger than the mass itself, yeah, you can always take the pi to the 4 as the leading order. So you are pretty close to here.
Okay.
So if you sum them up, so you may sum this and that, then you may be somewhere here. That's also so it's not easy to realize the realistic model in by summing up the polynomials.
Okay, thank you.
Thank you. Okay, good. So now I change my answer if Higgs can be the inflaton. Yeah, my answer is yes. And even more, Higgs gives the best fit of the Planck data. Okay, what does it mean? So here, this is the prediction from the R-square model, or Starobinsky's inflation model. And I will show you this prediction is exactly same in the Higgs inflation. They are actually the same models. That's what I'm going to talk about from now on. Okay, so if you accept this part, Higgs inflation gives exactly same prediction with the Starobinsky's inflation. You can easily see the Higgs is Higgs inflation located right at the point, the sweet spot inflation model right now. So among hundreds of models, Higgs inflation gives the best fit. Okay, it sounds strong, right? But yeah, that's the data. That's the data. If you look at the data, that's the statement you can make. Okay, so Higgs inflation is well motivated from the particle physics and observationally preferred if you look at the cosmological data. So it is certainly worth looking into more details. Good. So now I want to show you why Starobinsky's inflation model is same as the Higgs inflation model. Okay. So to do so, I want to go a little bit detour, and I want to consider the general non-minimal coupled inflation model. And that was considered K.H. Maeda many years ago, and also by myself. Okay. So let's start from the Jordan frame action. Okay. In Jordan frame action, I have Ricci skeleton here. So m Planck square is usual m Planck square. This is the scalar kinetic term. This is the scalar potential term. And if you look at this part, m Planck square has mass square dimensions. And in effective theory point of view, with the scalar field, you are actually allowed to write all this kind of terms, okay? So these are all mass dimension 2 operators. Well, in terms of the field, you can actually realize only phi squared term is allowed, okay? Then the coefficient is dimensionless, okay? But in general, you may write this kind of power law K term here, okay? So let's consider this frame. And if I only take n equals 2, that is 6 inflation. Oh, okay. So here n equals 0 is 6 inflation in this parameterization. Okay. All right. So now I set m Planck to be 1 to make my notation simpler. So this is the Jordan frame action I told you before. And I just replace 1 plus k by omega squared. And this omega squared is just the conformal vector in front of Ricci scalar. Once you see this kind of conformal vector, you can do this phi rescaling. So metric is rescaled by this same conformal vector like this. And G mu nu, upper G mu nu is omega minus 2 because this is the inverse of the G mu nu, right? And the determinant have omega to the 8 because you have 4 entries. And the Ricci scalar has transformed into this form. So omega square in front and R, okay? And also the derivative term of the log of omega squared here. And also the total divergence term, okay? So after getting rid of this total divergence term, you can realize square root of g omega square r, that is nothing but this term, right? The first term of the action. This term becomes square root of g and r, okay, without conformal vector. So r becomes canonical. And I have the log term here, and also other boundary terms. Okay, so by doing this phi rescaling, you recover the Einstein's frame where the gravity is canonical. I usually take Einstein frame action because I want to take gravity canonically behaving. Okay, and because of this log term, your scalar part is your scalar theory is modified, and I'm going to show you how it is modified. Okay, so this is the action. So in Einstein frame, I have the Einstein term. And from the log term, I have this term. Okay, by just taking the derivative log square, then I have this term squared. And I kept 3 over 2. Okay, that has 3 over 2 here. And from the kinetic term, the inverse of the kinetic term, I have omega negative 2. So I have this term in front of kinetic term. Okay, so I have the field dependent coefficient here, F, okay, and the potential. And potential has this scaling, omega to the minus 4. So I have this. So by doing this canonical rescaling, the phi is square root of phi. I can solve the H, and this H is canonical field. In terms of H, I have this canonical kinetic term and the potential. And this Einstein potential is now given by Jordan frame potential over omega to the 4. This is generic result, okay? So I can recover Einstein action with some modified potential. This is the non-minimally coupled theory. And then you can see very interesting results, the conclusion from this derivation, okay? So now, if k is increasing function, so just take monotonic function. Okay, if you take the phi to the phi square, this is of course a positive definite, and the potential is also the positive derivative potential is also positive definite in the inflationary time. Then you can see that Einstein frame potential becomes Vj of omega square, that is given by Vj over 1 plus k square. And because of this k, when field value is large enough, this whole term becomes Vj over k square. So you can read very generic condition for the flat potential. This is the condition, okay? Vj over k square, if this combination goes constant, you basically realize the inflation, okay? Very interesting. And then if you take the general power law, let's say potential is phi to the 2m, and k, the calorie is phi to the m, then this condition is realized, right? So in that case, you can easily see this model can accommodate the inflation. So indeed, you can check the actual shape of the potential for a different power m, okay? So power m equal 1, this is potential m equal 2, this is potential 3, 4, and so on. So you can always observe some power of here at large field value that the potential is actually flat. So over here, you can realize the inflation for different powers. And you can see this case, this particular case, m equal 2 is corresponding to the Higgs inflation, okay? Yeah, by the way, this is the power of so-called attractor solutions to the inflation. In this attractor solutions, you can see the predictions are converging into here. So NS is always 0.965, okay? Remember, this is the perfect value for the inflation, and the tensor to scalar ratio is 0.04 or 0.03, okay? This is also consistent with the current constraints about the tensor to scalar ratio. Current bound is somewhere here, 0.01. That part will be checked by the future coming experiments like Lightbird and so on. So I'm really looking forward to listening the results from the future experiments about tensor to scalar ratio, okay? And this is consistent with the Planck data. Okay, so now I want to show you why Starowinsky model and this model, the non-minimally coupled models, are equivalent, okay? Let's begin with this non-minimally coupled model again, okay? So this is the conformal term, kinetic term, and the potential, okay? During the inflation, kinetic term doesn't do much, okay? Because the potential is flat and phi doesn't move very fast. So yeah, let's take out this kinetic term for the moment. If you can neglect the kinetic term, you can regard the phi field as the auxiliary field, and you have learned you can get rid of auxiliary field by solving equation of motion in your school, right? So by taking the variation of the phi from this action, you get R phi R at the Cusi phi R from here, and from the potential you have lambda pi to the cube, and the equation of motion gives me pi square as Cusi R over lambda. Plugging in this result into the original action, you get this, okay? R from the original R, from the phi dependent part, you have r squared. Okay, pi to the 4 becomes r squared term. Okay, so this model, r plus r squared model, is nothing but the Starobinsky's model. And this model can explain the inflation if this parameter, QC square over lambda, is 10 to the 10. Or or the inversely, lambda over QC square is 10 to the minus 10. Okay, and that is set by this condition, Planck normalization. Okay, so in this regard, I would say Higgs can be the underlying theory of Starobinsky's R square inflation model, and the coefficient is calculable from the Higgs inflation, just non-minimal coupling and the self-coupling. Okay, very interesting.
Hi, Parker.
Yes,
Hi,
please.
Kuchen. If I include the higher order term of the R, does it also work for inflation?
Yeah, I have some discussion later on.
Okay, thank you.
Yeah, so basically the R cubed term and R to the 4th term, or all these terms can affect the results, right? And that can be converted into the shape of the potential at the end.
Okay.
Yeah.
Okay.
So if you stick to the standard model and the renormalizable part of the potential, lambda pi to the 4, then R square term is the highest order term you can have. So the R cubed term and R to the 4 term and so on, the high order terms in here should be small to realize the successful inflation.
Yeah, but it's a real strange because, okay, for example, R square term seems dominant compared to R term. Is right? Because this square over lambda is very large.
You mean this? Yeah, right. So if you just look at R and R square and very large coefficient here, that looks just weird, very weird, right? Yes. However, if you go back to the Higgs potential here, if lambda is small and QC is, let's say, order 1, then you can easily realize this relation.
Yes.
So in terms of the Higgs, renormalizable theory of the Higgs, then yeah, this parameterization is not that weird. So in that sense, yeah, that's why I want to tell Higgs can be the underlying theory of Starobinsky's R square model.
Okay.
Yeah, let's discuss more later. Okay.
Okay.
Let me just move on. Before going into further discussion, I also want to tell you how I can treat the f of r, okay, general term. It can, you may include R cubed term here, okay? So first claim is A f over r gravity is equivalent to a non-minimally coupled gravity plus non-dynamical scalar theory. Proof is very simple. Let's start from f of r. You can set the equivalent action f of phi plus f prime phi or minus phi. Okay, you can check the equivalence by taking the phi as the auxiliary field again. And by solving the equation of motion, you can set r equals phi is the solution. If you put this into your action again, you realize this action becomes this. So you see the equivalence. Okay. So the and also this theory looks like the non-minimally coupled theory already, because here f prime phi becomes this coefficient at the conformal vector omega square, and the potential is now given by the combination of f and f prime f minus phi times f dot derivative. Okay, so the potential is given here, and the conformal vector is given there. So f over r theory is really equivalent to this kind of theory, non-minimally coupled theory. Okay, and claim 2. A non-minimally coupled gravity plus scalar theory is equivalent to the Einstein gravity plus additional scalar. That's also pretty easy to see. Let's start from this non-minimally coupled theory, and this theory can be Boyle transformed into the Einstein frame. And in Einstein frame, I have additional scalar field S, and here S is sometimes called the scalaron, and scalaron is nothing but the log of omega square. Okay, and this omega square is the f prime, so I if I start from f of r theory, I can have this theory at the end. So this theory is nothing but Einstein theory plus scalar field with the potential. Okay, and the shape of the potential is also determined by the f. Okay, so potential in the Einstein frame is this combination. So now by combining claim 1 and claim 2, you realize that f of r is nothing but the Einstein theory with the scalar field degree of freedom. Explicitly, you have equivalence between f of r theory and the scalar theory with the potential. Okay, and I want to show you one example, r plus r squared. Yes, Starobinsky's model. By plugging in the same the machinery here, you can calculate the potential. The potential becomes this 1 minus exponential of minus 2/3 of s. Okay, so this becomes flat, and you realize inflation here. So this is in Starobinsky's model. And you can also check r cubed term. And here I set a very small gamma. In that case, I found that you start to move out from the acceptable range of the NS and R, okay, by taking large positive delta. Delta is the parameter. I didn't give the definition here, but that's nothing but the combination of these parameters. So by taking the negative delta or positive delta, you move out from the acceptable value. So gamma cannot be too large. So that was discussed in this paper. Okay, so now, yeah, you worry about the gauge invariance, but you shouldn't worry, because you can write down the gauge invariant action from the Higgs doublet or Higgs triplet, whatever. So in gauge invariant action, you can write down the non-minimal coupling term like this, and the potential. And by doing this, you already know this can be compatible with the inflation, because y to the 4 here, and the k is given by phi squared. So the condition I requested is really realized. So you can realize the inflation here. Okay, and this same model can explain the standard model electroweak symmetry breaking over in low scale. So you can connect the particle physics and cosmology by this single potential. That's the beauty of the Higgs inflation. Okay. So Planck normalization again can be realized by lambda over Cauchy squared. And in conventional model by Becherukov and Shaposhnikov, they considered very large non-minimal coupling and order 1 lambda, right? However, this is not really the case in the standard model, because in the standard model, lambda will run, RG run into the small number at high scale, indeed. So indeed, I would say this combination, the order 1 non-minimal coupling and very small lambda, is more compatible with the standard model observation. And I called it a critical Higgs inflation. And I think this is a very interesting particle physics based model of inflation. This is a review about the RG running of the lambda, the self-coupling. And this self-coupling is calculable by taking this loop diagrams. And in this loop diagrams, you see the gauge interaction term, and also the self-coupling term, and the Yukawa coupling term, and so on. And among all these terms, the second term is most important. Second term is coming from this diagram, and the top curve loop gives the large negative contribution, because top is the heaviest particle. So that couples to the Higgs standard model Higgs most strongly. So this term dominates. 6, by the way, comes from 3 times 2. 3 is color, 2 is the Higgs doublets. Okay, so by doing this, you see this term gives the negative sign of the beta function of the lambda, meaning the Higgs self-coupling becomes weaker and weaker at high energy. So this is the calculation from the Higgs self-coupling, and in this calculation, allowing the the experimental uncertainties from the LHC experiment, you can see the lambda indeed becomes small, and in near the Planck scale, this becomes almost zero. And also beta function of lambda becomes also pretty close to the zero. So indeed, we may see the Higgs criticality, lambda is zero and lambda prime is zero at high scale. This is open possibility, which is consistent with the current observation of the Higgs coupling. Okay. So in critical Higgs inflation, lambda is small compared to the electroweak value. Electroweak value of lambda is 1/8, as I told you, right? So if I take the combination of lambda over Cauchy square, lambda over Cauchy square at the critical energy is much, much lower than lambda over Cauchy square at the electroweak scale. So indeed, if this combination is 10 to the minus 10, you can realize the inflation. And one more interesting news from the ATLAS and CMS is the running coupling of the top quark. Okay, and this is the Yukawa coupling of the top quark measured by the CMS. And this tendency is really consistent with the critical Higgs inflation. Okay, lambda becomes smaller and smaller at higher scale. So top Yukawa becomes smaller, smaller. So by taking this pattern into account, indeed, the lambda, the self-coupling of the Higgs is really approaching to the zero at the Planck scale. Very interesting observation. So finally, I would suggest Higgs plus R square inflation model. Okay, so this is the model. Let's see. So this is non-minimal coupling term, the gauge invariant way. And lambda CC is, cosmological constant, which is not important during the inflation, but I just keep it. And R squared term, I wrote down this R squared term because you can realize, you can see that R has mass dimension 2 and R squared, the R has the length dimension 1 over length squared. So R squared term gives me the correct mass to the 4 the mass, the mass dimensions. So this, you cannot get rid of this term by your hand. Okay, even you set R squared term 0 from the beginning, this will appear by loop effect. Okay, so again, this non-minimal coupling term also appears by loop effect. So let's take this term and that term as generically allowed terms in effective Lagrangian. Then this is the setup you want to work on. Okay, and this setup is very interestingly giving me the naive cutoff scale is Planck or even higher. Yeah, maybe some of yes. Sorry.
May I ask one thing? So if the loop effects give rise to this R square term, would that also give rise to like aluminum square, like other curvature square terms?
Other terms, big Gauss-Bonnet terms and so on, right?
Yeah, well, Gauss-Bonnet is fine, but like aluminum, or like a Riemann tensor square.
Yeah, they can also appear, right? Yeah, but some of them can be packed with the Gauss-Bonnet term, and they can be negligible, as you said, right? So you don't have to keep all those terms. So you when you have R squared term, you do have one combination of Gauss-Bonnet term and aluminum, as you said, right?
Right.
Yeah, but in this game, I didn't take aluminum term explicitly, and in general, they can affect the inflationary dynamics. That's also true.
Right. And they introduce Gauss, right? It could be,
This just F over R is okay in terms of and so on. But as you said, those terms can be problematic in some sense. So so in my approach, those terms are somehow canceled out by some other mechanism.
I see. I see. Okay. Okay. Thank you.
Thank you very much. Yeah. Okay. So now let me say this is the setup I want to work on, effective setup, Higgs plus R squared term. And from this R squared term, it has the mass ms square, and this would be the mass of the scalar. Okay. Because of the time, maybe I should skip some of the explicit calculations, but at the end, I can realize the same action gives me the potential, the theory with two different scalars, one from the Higgs. Yeah, we started from the Higgs, so I have Higgs, and one scalar one from the R squared. So at the end, I have two scalar theory with this explicit dependence in the conformal couplings and so on. Okay, so now I have explicit model of two scalar inflatons. Then I can work on all kinds of phenomenology. Okay. Yeah. And one thing I want to tell you before closing my talk is about the naive cutoff scale. Just expand this Higgs potential in terms of small field, then you can expand all higher order terms, right? And if you look at the coefficients very carefully, the naive cutoff scale is just given by m Planck square over this square times ms square times m Planck. So if this combination m Planck square over Cauchy square ms square is larger than order 1, then you can realize a very large naive cutoff scale, and it doesn't bring any the problems in theory. Okay? And one thing is here, if you assume Cauchy parameter is large, very, very large, you may see this combination is not really order 1, right? On the other hand, as I told you, in critical Higgs inflation, Cauchy parameter is just order 1, okay? Maybe 10, 1, 5. In that case, this combination can be easily order 1 or larger. So you can safely make the theory behave very good at this cutoff scale in analysis. Very good. So now I have all explicit formulas, but let me just skip all these things. Okay. So believe me, Higgs R squared term has pretty good UV behavior and explain the inflation. Okay. Let me skip this. And finally, let me discuss a little bit about the phenomenology. Okay. In my eyes, Higgs R square inflation gives me a very good opportunity to get tested. First, because of the direct connection to the standard model Higgs, I can control the parameters in terms of particle physics of observations, Hopkong mass measurement, gauge coupling measurement, Higgs self-coupling measurement, all those measurements are relevant. And also in this two scalar theory of the Higgs R square, I can realize very interesting phenomena, so-called inflection point or ultra slow roll inflation on the way from the inflationary time to the later time reheating. Okay, if I realize nearly inflection point or ultra slow roll on the way, I can actually make the density perturbation enhanced a lot. Okay, so by having this density perturbation enhancement, I can make the primordial black hole production pretty easily. And also in this Higgs R square inflation model, I found the potential has tachyonic instability points depending on the parameters. And on the way of the inflationary evolution, if the inflaton meets the tachyonic instability, the perturbation near this documented instability can be easily grows. So by this growing the density perturbation, it will also generate the primordial black holes and gravitational waves. So I would say Higgs R2 has great chance to get tested by observing gravitational waves and PBH. And in particular, I found this Higgs R square model can accommodate the large primordial black hole production near here in this window. And this window is the window for the primordial black hole mass in between 10 to the minus 17 to 10 to the minus 12 solar mass. In here, the amount of the primordial black hole can explain 100% of dark matter. Okay, so if this is really the case, okay, Higgs R square model provide this possibility, then even you don't need to introduce any other dark matter component other than the Higgs. Higgs is just enough. Higgs explains the inflation. At the same time, during the inflation, primordial black holes are copiously produced, and they can explain dark matter, almost 100% of the dark matter amount. So this is also very interesting situation, I think. So if I look at this, I really want to tell, maybe we don't really need any BSM model because dark matter is explained by itself, the standard model itself. Okay, and also in the same parameter choices, I found the gravitational waves can be copiously produced in different frequency ranges depending on the parameters. So gravitational wave detection and PBH detections are two very interesting, very important observations which will confirm the Higgs inflation. Okay, so let me conclude. I started from the non-minimally coupled theory, and I enlarged it to the R squared term. And I told you I can introduce more terms, but more terms needed to be suppressed to explain the inflation and the Higgs phenomenon in general. Okay, and by taking RG running effect, self-coupling of the Higgs becomes small. So lambda over c squared can be easily 10 to the minus 10, and that can be consistent with the inflationary observation. And the theory becomes a unitary because QC parameter can be just order 1, and this whole parameter can be larger than the M Planck. So cutoff scale can be larger than the M Planck. So this model doesn't have unitarity issue at all. And PBH can explain 100% of dark matter. There are chances to get generating a lot of gravitational waves. And I didn't have chance to explain the leptogenesis and reheating, but they are built in a sense. Reheating is built in. Higgs couples to the all standard model particles, so Higgs degree of freedom can be easily converted into the radiation and particles. So reheating is not an issue. And I checked the reheating and also the preheating and so on, and Higgs R2 is pretty nice framework to explain all these things. And this model links electroweak scale physics and inflationary model scales. So we can learn from both sides, particle physics and colliders and astrophysics. Thank you very much. This is all. Torben, are you here?
Thank you so much, John. I'm sorry I was a bit had a problem with the button. Thank you very much for this really nice talk. Are there any questions in the audience?
I guess
And maybe yeah, Cheo.
Oh yeah, I just turned on my camera, but indeed I had a question. So I'm from cosmological point of view. So Stravinsky inflation is basically one of the subclass of the usual alpha attractor model provided by Andrew Linde. And so in the alpha attractor model, there's an additional one parameter which can bring all the chaotic inflation down to our arbitrarily small tensor to scalar ratio. So I'm I'm curious about whether you can use the similar trick here to introduce additional parameter to Higgs inflation and provide an arbitrary small tensor to scale ratio.
Well, in the Higgs inflation I told you today, I have only two parameters, right? Self-coupling parameter lambda and non-minimum coupling C.
Yes.
In this setup, I can fix everything. So you cannot make the tensor to scale ratio arbitrarily small. But you can introduce more terms, higher order terms, then you can change this a little bit. So you make the tensor to scalar ratio a little bit smaller, a little bit larger, but not very small. So this is the situation. And this theory is basically high scale theory, right? So tensor to scalar ratio tend to be large, but it cannot be very large. And the general prediction is 0.03, around 0.03 in Higgs inflation.
I see. Thank you.
Thanks.
May I ask something?
Yes, please.
Sure. About the running of lambda, I guess that running was computed without considering the gravitational loops, but there is this direct coupling between phi and r.
That's
so
right.
in principle, gravitational loops can contribute, but is there any? I don't know how to do it, and I'm not sure if anybody knows how to actually do the correct calculation, including the gravitational loops. But is there any proposal or calculation or some speculation about the contribution from the gravitational loops?
Yeah, there have been several attempts to include the non-minimum coupling directly to the loops. And the results is that still that contribution is subdominant compared to the top-core loops. Top-core loop is already order 1, so they are almost always winning over all other contributions.
I see.
So, yeah, there have been some papers. Yeah.
I see. These are all perturbative calculations, or
yeah, they are. Yeah, these are perturbative calculations. Do you think non-perturbative effect can be significant here? Well, okay, so this is important. So when non-minimum coupling is large, 10 to the 4, then that contribution can be even enhanced, right? But on the other hand, in my setup, critical Higgs inflation, KC is not large. KC is just order 1. So in that case, that contribution cannot be too large.
I see. I see. I see. Okay. Thank you.
Thanks.
Are there any other questions? Maybe I have a question, but I'm not sure if you can answer this. I mean, you spoke mainly about cosmology and the modification. When we take black holes nowadays, I would assume that these modifications at earlier times might also have effects, or maybe even a bit larger effect on the observations now. Do you know anything about that? Can we draw any conclusions from black hole observations nowadays to some of the parameters in your equations?
So in this setup, I have scalars and conventional gravity, canonical gravity in Einstein frame. So in that sense, if you just take the scalars as the source of the energy momentum tensor, then the black hole by itself is just same as conventional Einstein gravity. Yeah, that's my answer. I think that's so Einstein frame is convenient frame to see the gravity behaves just normal, even though you started from non-minimal couplings.
Oh, okay. I mean, I'm not that familiar with cosmology. Why I'm asking. Thanks.
Thank you.
Rishikesh?
Hello, I have a question. Seong, very nice talk. I really enjoyed. So
Thank
you
you.
said you like the definition of inflation as a precursor to hot Big Bang, right? Let's say initial condition for hot Big
Yeah.
Bang.
Yeah.
Then what can be a initial condition for inflation? Is it I mean, in your opinion, is it a quantum theory of gravity or?
Yeah, very good question, of course. Yeah. So I have two feelings, two answers. One answer is so before the inflation, whatever it is, it doesn't matter. It doesn't give us any observational consequences because of the inflation. Inflation reset everything and set the initial condition for the hot Big Bang after the inflation. So I think that's the beauty of the inflation model. On the other hand, we can still think of what can cause the universe by itself, right? In that regard, I can have many imaginations, but I don't have any scientific answer to you.
So yeah, I like the first option, the one you suggested. Yeah. Thank you.
Yeah, I can imagine multiverse and baby universe and so on, but it doesn't
Or
matter.
a bounce maybe, or
Yeah, it doesn't give me PVH, for instance.
Mhm.
Are there any other questions?
Can I ask another one if you don't mind?
Sure.
So Higgs inflation and the Stravinsky equation essentially gives the same predictions for NS, R, and FNL at this fourth shape. How can you actually distinguish them? How if the observation power increases and how can we distinguish them, the two models?
If you just look at NSR and FNL, you never distinguish them. They're
Right.
just same theories.
Mhm.
The only chance is to see the kinetic part of the Higgs more carefully.
Mhm.
Yeah, that part. And if we stick to the slow roll timing, you don't really distinguish them. Yeah.
I see, but can you, if the running of the spectral index, does that help? Or
Yeah. So at the end, actually, I showed you the Higgs plus R squared term. I want to use both. So indeed, in effective theory point of view, you want to keep both. Yeah. So in that case, the interpretation of R squared can be different from the interpretation I gave you. R squared term by itself is just independent term appearing from the loop corrections, for instance. So then I really have additional field degree of freedom, scalaron, and Higgs. So you have two scalars in the play. They generate interesting phenomena like PBH production.
I see. I see.
Yeah. So so now in my last conclusion is that Higgs R2 looks good. It doesn't have any unitarity issue, and it is consistent with the critical Higgs inflation, and it can generate all interesting phenomena like PBH and gravitational waves. So these days, I really focusing on our Higgs R square and modification of Higgs R square inflation. Yeah.
Okay, I see.
So I think reheating can also distinguish them, right? Because
Reheating, yeah, right. Yeah, if it is really the Higgs, then Higgs has a particular reheating pattern. Yeah, that's true. That's true. Yeah.
But we cannot really observe reheating directly, right? I mean,
yeah, no.
that's another.
Yeah, that's the problem. Yeah.
Are there any other questions? If not, then let's end the official part here. Thank you very much again for this nice talk.
Thank you very much.